Hello, welcome viewers. So we shall discuss about the numerical techniques, computer-oriented numerical techniques and the statistical techniques in this session. It means how to teach the basic arithmetic to the computer. That's we know the basic arithmetic, that's plus, minus, multiply, and most important is the flotation of the decimal. We know it, but how to teach it to the computer, that first of all we will discuss in this topic. Then we will apply them on the mathematical or numerical techniques of which are oriented by the computer. It is a very interesting topic. We take a very simple example. Let us say 5 divided by 2. If we ask anyone 5 divided by 2, immediately he will reply, it is 2.5. It is 2.5. That's correct. Because we joined the school in the basic classes and we were taught there this is equal to this. But when we ask a computer, he will show the result 5 by 2 is equal to 2. And what is the difference? It is the difference between our arithmetic and the computer arithmetic. Then how to synchronize both the concepts so that what do we want the computer say the same thing. For that, we consider the significant digits. There are significant digits or figures. So our computer system, it is familiar with these significant digits but not with our real number systems. So if we want to get this result from the computer, we will have to change this figure like this: 5.0 divided by 2.0, then it will give the result 2.5. Now we say, what is the difference? After decimal, 0 has no value, but it is in our mathematics because we were in the school during the basic classes. Then how to teach it the computer? First of all, the significant digits. Let us consider about some figures. Say here we write digits or numbers, and here significant figures or the digits. Simply how it counts. Say number 2, it is significant digit 1. 27, significant digit 2. 385, significant figure 3. No, 3850. That's the problem. We count, these are the 4 digits, but in significant language we say they are 3 significant digits. So what's about this? 0.2, again significant digit 1. 0.20, significant digit 2. 0.200, significant digit 3. But it's 0.02, significant digit 1, 0.002, significant digit 1, but 1.002, significant digit 4. It means the computer does not consider the zeros between the decimal and the first digits. Here, these are the significant digits which our computer system follows during a arithmetical calculations. Now here see some particular figure, say we want to write 5,000. No, it is an ambiguous figure for the computer. It is a complexity. So you see this figure, it is a complex figure for the computer. How it will count? Then again I repeat, here are the given numbers. Number 2, significant figure 1, number 27, significant figure 2, number 385, significant number 3, 3850, again significant figure 3. It means the zeros in the last, that is not counted by the computer system. 0.21, 0.20, it will be counted. 2, 0.200, it will be counted. 3, 0.02, only 1. This 0 will not be considered by the system. Similarly here, 0.002, its significant digit is 1. Rather, we can say in our simple arithmetical language, we have calculated this figure up to decimal 3 place, but it has only one significant digit. But in this case, 1.002, there are 4 significant digits, but we have calculated in our arithmetic this calculation up to 3 decimal place. So by considering these figures, we reach at this particular figure, say 5,000. How to represent it? We know it is 5,000, but how our computer system will recognize it? It is a very complex figure for the computer system. From this point, we start the computer arithmetic. Then we represent any number, say n is equal to m into 10 raised to the power e. M stands for mantissa. M stands for mantissa and E stands for exponent. E stands for exponent. So we decided a system that we will represent every figure. We will represent every figure in this form, mantissa into 10 raised to the power exponent, so that our system could identify every figure in the same manner. Let us see, this 5,000, we can write it 5 into 10 raised to the power 3 in this form. What we will follow? Like this. It is the word of the real numbers. Here we say it is a decimal or decimal. Decimal flotation in a computer arithmetic, it is a very rigid problem. How to move it? If we move the decimal towards the left, then it gives the positive exponents. If we move it to the right hand side, it gives the negative exponents. Let's see, in this case, here 5,000, we replaced 1, 2 and 3 place. 5.5 into 10 raised to the power 3 place, that is the plus 3. So we decided that every figure which we will represent, we will give him computer a program in this way. Now, further, what problems arises? Let us say it is a figure, say 0.0028785.6. It's a number. How to represent it? how to represent it in the standard form, that we say it is the normal form. It is the normal form. Let us see. That is equal to 2.87856 into, we have replaced the decimal from here to this place. 1, 2, 3. 3 place on the right side. Then we write 10 raised to the power minus 3. So again we consider some other examples. Say n is equal to 8526.7.9824. We represent in the in the normal form, that is, here is the decimal, we replace it here, 8.52679824. How many places? 1, 2, 3 and 4 places they have been replaced on the left hand side. Then we write into 10 raised to the power 4. In the normal form, the mantissa, the value of mantissa, it is the mantissa. Its value is from 0 to 9. We can't place 2 digits before the decimal. We always keep only single digit from before the decimal, and that is the normal form. But we can write also in this way, in the exponent form. Write this 8.52679824 E4. E stands for exponent. Sometimes this figure is written in this way. If it is a negative, we can represent this negative formation like this: 2.87856 E-3. It is a presentation of the negative figure and it is a presentation of the positive exponent in the exponent form. No, we see there are only 4 digits. We can write in this way. It means mantissa has only 1 digit. No, after mantissa, no, we see there are 1, 2, 3, 4 and 5 digits. Here after mantissa, in mantissa there are 1, 2, 3, 4, 5, 6, 7, 8 digits. There is no limit. There is no limit of the digits after the decimal. That's again created a problem for the system, how to identify them. So we bind the system to a particular system from this normal presentation to floating point representation. How we represent a figure in the floating point representation? Same. We say it is 8 decimal floating point, 8 decimal floating point representation. That is the standard form. What we use in our system, 8 decimal floating point representation. Here we write the figure only taking the 8th place. They say 1, 2, 3, 4, 5, 6, 7 and 8. The first column, it is for the sign, either plus or minus. and these 4 places, they are for mantissa M1, M2, M3, M4, and again this place is for sign of the exponent, and here we write exponent E1 and E2. 1, 2, 3, 4. It is the standard presentation of any digit in the 8 decimal floating point representation. Its benefit is, its advantage is, or one to say, the computer system can identify every digit under this rule. We will discuss this. Let us see. We want to represent here the mantissa. M stands for mantissa is always less than 1 and greater than or equal to 0.1. It is somehow different from the normal form. In the normal form, the mantissa was between 1 to 9, between 1 to 9. No, we change the concept. We say keep the mantissa between 0.1 and 1, and 4 places for mantissa and 2 places for exponent. Now again we repeat the same which we studied few minutes before. Let us see. There is a figure, say it is 2875.38287. We want to represent into the 8 decimal floating point presentation, which is the standard system to study the arithmetic in our computer system. Here, what do we see? The mantissa lies between 0.1 and 1. So, this decimal, we will have to shift this decimal to here. It means point starts from here. Its sign is positive. But mantissa can have only 4 values. But they are 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what we do? We have 2 options. Round off, either round off the digits or chop off. Chop off means remove the remaining digits except 4. That is chop off. If we want to round off, let us see, if this last figure is greater than 5, we increase this figure by 1. Say it is 7, it is greater than 5, we will count it 9. Of 9, it is greater than 5, we will count this figure as 3. If the figures are less than or equal to 5, then we do not alter the figure. No, it is 3, we don't alter this figure, it will remain 8. No, it is 8, it is greater than 5, we will consider it as 4. No, this 4, it is less than or 5, so we keep this 5 as a 5. Now, here are the 4 mantissa. We can represent this number in the 8 decimal floating presentation: 1, 2, 3, 4, 5, 6, 7, and 8. Here was the decimal. We shifted the decimal 1, 2, 3 and 4 places. 1, 2 and 3, 4 places on the left hand side. It means 10 raised to the power 4. Again I write, if we replace the decimal towards the left, it will give the positive exponent. If we move it towards the right hand, it will give the negative exponent here. So how we write it? First of see, its sign is plus. After that, 4 places for mantissa. 2, 8, 7 and 5. Where the others are gone? Others are dissolved either in this method or in this method. Here we are following round off method. Next we say it is the sign for the exponent. Exponent has the sign plus. And what is its value? Its value is 4. Then we write it is 0 and 4. It is the presentation of a number in the 8 decimal floating point representation. So our system follow this rule and it reads the every figure in this way. It means if the figures are more than 4, then it will round off or it will chop off according to the given program, and that will be the representation. Let us see one more example on this. Say it's 0.002875679. We want to represent it into the 8 decimal floating point representation. Here we know our mantissa lies between 0.1 and 1. It means before decimal there should be no any digit. It means we will have to shift this decimal to this place. How many? 1, 2, 3. 3 place on the right hand side. It means exponent 10 raised to the power minus 3. In mantissa we can keep only these 4 digits. But what's about these 2? Now we round off them. If we round off them, say it is 9, it is greater than 5, we count it as 8. If it is 8, it is greater than 5, we count this as a 7. So we write this figure in this way. We draw again 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. See, here the digit is negative. Minus, we write mantissa 2, 8, 7. It is 7 and it is 6. 2, 8, 7, 6. Why we got the 6 here? By round off. In 9, it is greater than 5, we count it as 8. 8 is greater than 5, we count it as 7. And 7 is also greater than 5, we count it as 6. That is round off. If we have to chop off the figure, then simply we erase the last digits. Next we see the sign for the exponent. Now sign is negative and exponent is 3. Then we write it as 3. That is a representation of any number in the 8 decimal floating point representation, or we can say how we teach our system the computer arithmetic, so that it may identify each and every figure which we want from it. But everywhere there are the limitations. Rather, computer is also a machine. It has everywhere limitations and we have to cooperate with it. Let us see what is the limit here. See, we have left only 2 places for exponent. We have left only 2 places for exponent. But it means we can consider only plus 99 and minus 99. It is the minimum exponent and it is the maximum exponent which can be stored under this system. If our calculation say gives the exponent 100, that's the problem. We cannot represent the 100 because we have provided only two places for exponents. Similarly, here, if the exponent is minus 100, our system will not store it. Our system will not store it, and they will not show any calculation, and that will create the typical or the complex situation for the system. Then how we control this situation? We control this situation by saying it is the overflow and the underflow of a computer. Now, this figure, if it is greater than 99 or it is less than 99, then we see again this format is in trouble. So how we cooperate with this problem? We cooperate this problem with overflow and underflow. So we can we will discuss about the overflow and the underflow of the computer. That is some calculations. Before understanding that, we say there are the two digits, say n1 is equal to 208.36.
When we plot the line,
No, let us discuss about the limitations of this system. It's 8 decimal floating point representation, rather it is the better than the others we are using at present, but it has also some limitations. That's why I told before this, what will happen if the exponent is more than 99 or it is less than minus 99, how we control that problem. Let us see few examples. Say here n1 is equal to 0.6705 into 10 raised to the power minus 99, and n2 is equal to 0.6685 into 10 raised to the power minus 99. Here we have two figures. They are in the 8 decimal floating presentation form. We can write them in this way: plus 6705 minus 99. And second figure in the same manner. What will happen if we subtract both the figures, n1 minus n2? Then it will give 0.0020 into 10 raised to the power minus 99. But it is not in the 8 decimal floating point representation. For that, we will have to shift this decimal at this place. It means two places on the right hand side. So we write it in this way: 0.2000 into 10 raised to the power. If we have shifted it on the right side, we will add minus 2. It will become minus 101. The remaining two figures, they are written to fill up the 4 places for the mantissa. No, here is the problem. This figure cannot be stored under this system. Then we stop the system here. The count it 0. Count it 0. If any figure which is less than, whose exponent is less than minus 99, computer will count it as 0. It means the 0 of the computer doesn't mean nothing. It means it is something, but our system cannot consider or count it. That is the difference between the arithmetical 0 and the 0 of the bits which we use in the 32 bits representation. It means that zero of a computer does not mean nothing. Zero of computer means there is something, but our system cannot consider it, cannot count it, cannot identify it. We count it, we say it is the underflow. It is underflow. It means underflow is controlled by using the figure 0. Then what will happen if this figure increases more than 99? Let us see some other example for that. Say x1 is equal to 0.2004 into 10 raised to the power 47, and x2 is equal to 0.119 into 10 raised to the power 55. If we multiply these both digits x1 into x2, we get 0.02243 into 10 raised to the power 102. No, that is equal to 0.2243 into, shift the decimal at this place, into 10 raised to the power 101. Again the problem, the exponent exceeds the figure 99, or it is 101, our computer cannot store it, and we say it is the overflow. It is the overflow of the computer, and here is the problem. There is no control for such situation, so we must be familiar with the format or the minimum limitations of our computer system when we are doing any arithmetical problems on that. It has no control, but underflow can be controlled by 0, it cannot be controlled. Now it is overflow and the underflow of a computer in the 8 decimal floating point representation. Now we will discuss the basic arithmetic of the computer, or we say main computer arithmetic. Let us see simple. Say here x1 is the figure, that is 20.2787 into 10 raised to the power 2, and x2 is the figure, say 0.04582 into 10 raised to the power -1. No, what is x1 plus x2? Remember that arithmetic we are studying, it is not our arithmetic. This arithmetic is for the computer system. How the our system will deal with this problem, that's we are going to discuss. It does not mean we multiply this figure by 10 by 2 or this figure by 10 raised to the power -1. That is ridiculous. But we have to see only how our computer system deal with this problem. Our computer system has got a particular system, that is the 8 decimal point representation, and it will follow the same system. That's how, if we write it this 20.2787 into 10 raised to the power 2 plus this figure 0.0045862 into 10 raised to the power -1. Then how our system will calculate it? First of all, the problem is for the exponent. Here the exponent is +2 and here the exponent is -1. First of all, these exponents, they will be equalized. How we know our system? That is the real number. Here is the decimal on this side plus, on this side minus. We have two options. Either we can convert 2 into -1 or -1 into 2. Both options are equally good. Rather, say we want to convert this 2 into minus 1. Let us say 2 is equal to minus 1. How it is possible? If we do 2 minus 3. 2 minus 3 means minus 1. Minus means this side. It means in this figure we displace the decimal up to 3 place on the right hand side. That is 2278 point. No need into 10 raised to the power 2. That 0.7. Why? When we have to convert 2 into minus 1, we are going to convert 2 into minus 1. 2 is equal to minus 1. It's simple arithmetic. If we do minus 3, 2 minus 3 is equal to minus 1. Minus 3 means displace the decimal towards the right side for the 3 places, 1, 2 and 3. That will become into 10 raised to the power minus 1 plus 0.0045862 into 10 raised to the power minus 1. Now exponents are same. We can take common. It is 20278.7 plus 0.0045862 into 10 raised to the power minus 1. Until or unless the exponents are not same, in computer arithmetic, addition and subtraction, it is the major problem. But multiply and division, they follow the same rules, basic rules of the indices, or you can say the rules of the exponents. Now if we add them, that is 20278.7 plus 0.0045862 is equal to, that is 20278.7046 into 10 raised to the power minus 1. It is not the final calculation, because thus we know these calculations, it is done by our system. We will have to convert into again 8 decimal floating presentation. For that, what we do? We will have to shift this decimal here. How much place? 1, 2, 3, 4 and 5. Plus, we will write 0.202787046 into 10 raised to the power minus 1 plus 5. 1, 2, 3, 4 and 5. Still it is not in the standard form. So we round off this figure like this. Here it is 6, we count it as 5. It is 5, it is 1. It is 7, it is 9 and it is 8. So we can write it plus 202.8 plus 0.5. It is the complete calculation that the our system will follow under the format 8 decimal floating representation. Same is the problem with the subtraction. We have to synchronize, or we have to equalize the exponent by using this basic rule, either shifting on the right side or shifting on the left hand side. Let us see some more examples. Say let A is equal to 0.2222 into 10 raised to the power 2 b is equal to minus 0.1001 into 10 raised to the power 3 and c is equal to 0.1002 into 10 raised to the power 3. Then here we check the law of distributive. Check the law of distributive. It means show A cross B plus C is equal to A into B plus A into C. That is all the things we studied. It will follow each and everything in this problem. Like this, let us say A is equal to this. First we take left hand side, that is equal to B plus C. B, it is minus 0.1001 into 10 raised to the power 3 plus 0.1002 into 10 raised to the power 3. We see both exponents are same. If they are same, minus 0.1001 plus 0.1002 into 10 raised to the power 3. Then we have no need to shift the decimal either on left or on the right hand side. Here that is equal to 0.0001 into 10 raised to the power 3. If we subtract them, then it is a complete A cross B plus C. That is equal to what is A? 0.2222 into 10 raised to the power 2 multiplied by 0.0001 into 10 raised to the power 3. That is simple. In the multiply, bases are same, powers are added. That is equal to 0.2 2.222 into 10 raised to the power minus 5 plus 5. 3 plus 2, that is 5. That is equal to 2.222 into 10 raised to the power 0. So we can write it in the normal form like this. So left hand side, that is equal to decimal 2 into 10 raised to the power 1. We have shifted the decimal towards the left hand side. Now here it is the left hand side. Now we check out about right. In that, first we find A cross B or A multiplied by B. That is 0.2222 into 10 raised to the power 2 multiplied by minus 0.1001 into 10 raised to the power 3. That is minus into, first of all, this power added 10 raised to the power 5. And if we multiply these both figures, that will give minus 0.022222, and we can write it in this form minus 0.222422 into 10 raised to the power 4. Then A cross C, that is 0.222 into 10 raised to the power 2 multiplied by 0.1002 into 10 raised to the power 3. That is equal to, first of all, exponent added 3 plus 2, 5, and it will give 0.02226444. In standard form, it is 0.222644 into 10 raised to the power 4. Now, last step of addition, that is A multiplied by B plus A multiplied by C. That is equal to minus 0.222422 into 10 raised to the power 4 plus 0.222644 into 10 raised to the power 4. Again, the exponents are same, so no need to shift the n decimal. 10 raised to the power 4 we can take common, and it will give, that is 0.0002. So we say left hand side is not equal to right hand side. So it is right hand side and it is left hand side. They both are not equal. In the same way, we can prove any result in the computer mathematics. Sometimes the problem is, in some books you will find, we write the figures in this way, but they write the figure like this. A is equal to 0.2222E2. And if it is negative, say, let us see. C is equal to 0.1002E minus 3. So there is nothing to confuse. These are the same, the representation for this. For positive, we do not add any sign. For negative, we add hyphen. Either some books you will see hyphen here, in some books you will see hyphen before E. Both are same. Again, the calculation is in the same manner. That is some basic about the computer mathematics. But now we have seen, when we write over numbers in the 8 decimal representation, we follow the two concepts, that's the round off and chop off. But what we think, that is clear. If we round off any figure or chop off any figure in the scientific calculations, it will create a great problem. Then how to deal with them? It means these standard formats, they create the errors. Now we will deal with these errors, how and how much the error is created, and how we consider it, how we calculate it, then how we adjust it with our final calculations. Let us see about the errors produced in the computer arithmetic due to the conversion of the given digits into the 8 decimal floating representation or any standard format in our system. Here we discuss the 3 types of the errors. See, first of all, it is absolute error. Absolute error. And we denote it by E small a, that is modulus of actual value minus approx value. Approx value, how we will get approx value? By round off or by chop off. And magnitude means it is positive. Why? The errors created in our arithmetic, they always affect our calculation always positively. Second, it's the relative error. Say ER, that is equal to actual value actual value divided by absolute value divided by actual value. If we divide the absolute error divided by actual value, we will get the relative error. Then percentage error. Percentage error we denote it by EP, that is relative error multiplied by 100. These are three types of errors which we discuss by number system and in the algebraic system more in the different manners. First we discuss them into the arithmetical or the number system. That is, we say take a simple problem, say if 2 by 3 is approximated by 0.667, then find relative error. That's the problem, say simple. If we divide 2 by 3, we know it is a it will give the non-terminating fraction 0.6666666. But at some place we will have to stop it. Say it is 0.667. Now first we find first of all absolute error. Absolute error, that is equal to actual value minus approx value. That is equal to 2 by 3 minus 0.667. Here we see we keep our figure fraction in the same manner. Rather it is 2 by 3, it is 1 by 3, or sometime it is pi 22 by 7. If we will calculate it again, it will give this figure and answer will be 0. So we do not change the given situation of the given any figure. Now we can take LCM in this 3 into 2 minus 0.667 into 3, that's equal to 2.001. That's equal to 0.001 divided by 3. It's always positive. If it divided by 3, that comes to be, that is equal to 0.00333333. It's again non-terminating. That is the absolute error, but we are interested in finding relative error. That is absolute error divided by actual value. That is means EA 0.00033333 divided by 2 by 3. That's equal to it's equal to 0.00099999 divided by 2, and that's equal to, that is divided by 2, point 0.0049999. That is the relative error. If we want to find the percentage error, we can multiply it by the 100. In this way, we find the errors in the number system. Let us see some more example on this in the different manners. Say, find the relative error. Find relative error in figure 834.123 correct to 5 significant figures. Five significant figures. Now here we will have to keep in mind that we are going to consider the significant figures. Now here it is the actual value that is equal to 834.123 and we denote it by say XA. But these are 6 significant digits, 1, 2, 3, 4, 5, 6. But he wants 5 significant. Then we get approximate value. Approximate value, we follow the rule of round off. How? It is 3, it will remain 2. 834.1 and 2. Say it is X. It is 3, it is less than 5, so there is no change in 2. Now we can find absolute error, that is equal to XA minus X, and that is equal to 834.123 minus 834.12, and that's equal to 0.003. Then what is relative error? That is EA upon actual value XA. 0.003 divided by 834.123, and that will give relative error, that's come to be equal to 0.0004068. We can leave it here or we can represent into the 8 decimal floating presentation. In such a manner, we can find the errors in our numerical system. Now, how we will deal in the algebraical functions? That is the somewhere different way. Say, we say evaluate relative error ER of function say x y square z. It is a function if x is equal to 1, y is equal to 2 and z is equal to say 2.5, z is equal to 2.5, and given delta x, small change in x, that is equal to 0.5, delta y is equal to 0.4 and delta z is equal to 0.1. It is the formation of the problem in the algebraical functions. How we can find the relative error in this way? Now we will have to change the our path which we followed in the numerical system. No. Here we follow the rule. First of all, say what is relative error. Its formula is, that is delta f divided by f. Delta means partial differentiation of the given function. Take it, say number 1, say then what is delta f? Delta f is equal to curly f by curly x into delta x. We read it curly. Curly means not differentiation, it is the partial differentiation. Partial differentiation means we will differentiate only that part of the function which contains x. Then plus curly f divided by curly y into delta y plus curly f divided by curly z into delta z. If there are only two variables, we will not consider. If there are four variables, we can extend this. So this formula is flexible. We can reduce it and expand it. Curly means, again I say, it is the partial differentiation of only that variable which is present here. That is curly f by curly x. If we differentiate it, then we shall differentiate only here. We write the function f of x or is equal to x y square z. Differentiation for x, that is equal to 1. We write it y square z into delta x plus differentiation with respect to y, it's partial. We shall differentiate only y square, that is x into 2y into z. Both variables, they are not altered at any cost, into delta y plus curly f by curly z, only differentiation of z, that is x into y square into delta z. Now we can put the given values. These all are the provided in the problem. Here value for y, here y is equal to 2 square means 4 into z 2.5 into delta x 0.5 plus x 1 into 2y. 2y means again 4 into z 2.5 into delta y 0.4 plus x 1 y square, again it is 4 into delta z, that is 0.1. Now we can calculate it. That is 2.5 into 4 into 0.5, that's equal to 5. We are calculating delta f, that is 5 plus it is 4 into 2.5 into 0.4, that's equal to 4 plus 0.4, that is equal to 9.4. It is delta f. Now, who is f? F is the given function x y square z. We can calculate it by putting the values. Here x is equal to 1 into y is 2. 2 square means 4 and z means 2.5, and that's come to be 10. Then what is the relative error? That is equal to from 1 delta f divided by f, that is equal to 9.4 divided by 10, that is equal to 0.94. That is a simple one, but the way is the totally different which we followed in the numerical systems. That is the way how we can find the relative error in a algebraical function. It may be 2 variable, it may be 3 variable, 4 variables, anything, but these values will be provided to evaluate it. That's about the errors. No, there is some special type of error. It was in the number systems. No, in mathematics, we also deal with the power series. Say, let us take an example. Power series means expansion of, say, e raised to the power x, sin x, cos x, Taylor series, Maclaurin series. There are so many series. Say here we say expansion of e raised to the power x, 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial plus x raised to the power 4 upon 4 factorial plus so on. Then how we calculate it? If we want the convergence of series, then how we calculate it? Or we say if we want to put x is equal to 1, e raised to the power 1, that is equal to 1 plus something something, we will have to terminate the series at some point. And if we say terminate the series after this, and if we consider only these three terms, the terms which we deleted, it will create the error. This is the particular type of the error and it is called the truncation error. It means truncation errors, they are generated only in the power series. Say truncation error. And how to deal with them? We will deal them in the power series like this. Say let us discuss an example for the truncation error, that is find the truncation error in expansion of e raised to the power x by terminating four terms at x is equal to 1. These are the two main things which are provided in the problem. So by terminating 4 terms, by terminating 3 terms, by terminating 7 terms, and how we deal with it, say, right, we take the expansion of e raised to the power x, that is 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial plus x raised to the power 4 upon 4 factorial plus x raised to the power 5 upon 4 factorial and so on and so on. At x is equal to 1, that is e raised to the power 1 is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial plus 1 by 5 factorial plus so on. How much terms should we contain according to the problem by terminating 4 terms? 4 terms means 1, 2, 3, 4. We don't count it as a term, it is a constant. It is a constant. It is separate. Other than 1, these are the 4 terms. Then we say e is equal to 1 plus 1 plus 1 by 2 plus 1 by 3 factorial means 6 and 4 factorial means 1 by 24. That is equal to 2 plus 0.5 plus point. We can calculate it. 1 divided by 6, that is equal to 0.1667 plus 1 by 24, that is equal to 0.0141 and 7, that is equal to 0.5 plus 0.1667 plus 0.0417, that is equal to 2.7084. It is e raised to the power 1 that we calculated. We means our system calculated by terminating the 4 terms. But if we check the value of e raised to the power 1 from the table, or if from your system calculator or computer, its value is 2.718. Take it number 2. Then how to find the truncation error? Then truncation error is equal to, what we see, actual value minus approximate value. Again, actual value is 2.718 minus 2.7084. Same formula which we followed in the absolute error. True value minus approximate value, and that will give you 0.0097. In this way, we find the truncation errors in the power series. This power series may be e raised to the power x, or any trigonometrical, or any Maclaurin's, or the Taylor's expansion. But here in our topic, computer oriented numerical techniques, this example is the most important example for the truncation error. So viewers, it was regarding the computer arithmetic, how our computer system follow the arithmetic. It means how we will teach the computer this arithmetic so that it will give us the exact calculation, and most important is that we must be familiar with the limitations of the format of our system, how much calculations it can count or it cannot count. So we have seen the most important points about the zero. In the zero of the computer does not mean there is no value, it means there is something which our system cannot count. That can create the trouble for when we are dealing with any type of the scientific calculations. Now we will apply these systems into the further calculations or the further problems of our numerical techniques. Say, let us discuss an example. Rather, it is very simple. You would have studied during the school level. But no, we are not going to calculate it. These calculations which we will do, we expect this calculation from our computer system. We do not need to calculate it, only what we want, how our system will calculate this problem. Rather, it is a very basic problem. We say find the value, solve the equation x square minus 1000x plus 25 is equal to 0. Solve the quadratic equation. Use, it is 4-digit Mantissa. Using 4-digit Mantissa. Remember, 4-digit Mantissa means, again, that system which we studied, 8 decimal point floating representation. It is a simple quadratic equation. In the school level, we know the formula, that is x is equal to minus b plus minus under root of b square minus 4ac divided by 2a. Then we can calculate it very in simple way, in this way. But again I repeat, these calculation we have not to calculate. These calculations, they are done by the our computer system. How it will follow the steps according to this system, which is the system used by our computer. 4 decimal या 4 digit Mantissa. Let us say x is equal to, again we follow the same rule for the roots, that is minus b plus minus under root of b square means 1000 square minus 4 into a into c divided by 2a, that is equal to 1000 plus minus under root of 10 raised to the power 6 minus 10 raised to the power 2 divided by 2. Or we can write it, that is equal to 10 raised to the power 3 plus minus under root 10 raised to the power 6 minus 10 raised to the power 2 divided by 2. Now, this is calculated according to that formula. No. Further calculation, they depend upon this given system using the 4-digit Mantissa. Then we will have to convert these figures into the standard form, that is the 8 decimal point representation. Let us say, first of all, say what does mean 10 raised to the power 6. 10 raised to the power 6, we can write it, that is 1 into 10 raised to the power 6, and we can write it 0.1000 into 10 raised to the power 7. 4 place digits, 4 Mantissa, 1, 2, 3, 4. The remaining way 3 we filled with the 0. Now see 10 raised to the power 2. 10 raised to the power 2, we can write 1 into 10 raised to the power 2. That is equal to, say, 0.1 into 10 raised to the power 3 by shifting the decimal. Now, if we subtract them, 10 raised to the power 6 minus 10 raised to the power 2 means 0.1000 into 10 raised to the power 7 minus 0.1 into 10 raised to the power 0.1000 into 10 raised to the power 3. We know we cannot subtract these figures until the exponents are same. So we change 7 into 3. Here is our format decimal, here it is plus, it is minus. Then 7 minus 4 is equal to 3. So we replace this decimal towards left for the 4 digits, 0.000100 into 10 raised to the power 3 into 10 raised to the power 3 minus 0.1000 into 10 raised to the power 3. If we calculate them, that will give us 1 into 10 raised to the power 3, that is equal to 0.1000 into 10 raised to the power 4. It is the standard form. These are the values. Now we have to find the roots of the equation here. So x is equal to 0.1000 into 10 raised to the power 4 plus 0.1000 into 10 raised to the power 4 plus minus divided by 2. That is x1 is equal to 0.1000 into 10 raised to the power 4 plus 0.00 into 10 raised to the power 4 divided by 2, and that is equal to 0.1000 into 10 raised to the power 4. if we consider the second root, that is 0.1000 into 10 raised to the power 4 minus 0.100 into 10 raised to the power 4 divided by 2, that is equal to 0. But that is the not answer. 0. It is why the 0 has created. It is the subtractive cancellation, because the both figures are too close, though they produce the 0. Now to find the second root, we follow the another system. If this is the condition, that is say, then product of the roots x1 into x2 is equal to c upon a. That is given condition, that is 25 upon 1. We have to find x2. x2 is equal to 25 upon x1. Now here we put the value of x1, then we get x2. So we cannot consider this 0 as the root, because it is generated due to the close occurrence of the figures. It is the subtractive cancellation error produced. That's about the computer arithmetics and some its application. Any question about this? It is the basic computer mathematics, we say, that are the computer oriented numerical techniques. And we will continue this next time. Thanks and good day, viewers.